Okay, good afternoon everyone and welcome to this Licentiate Seminar. My name is Sebastian Bara. I'm an associate professor at the Department of Computer and Electrical Engineering, and I will be the chairman for this seminar. So I will shortly introduce you to the key players in this seminar, as well as the general process, how this will go on. And then I hope that you will enjoy the seminar. So, of course, as one of the main key persons in the seminar, we have Yuxuan Zhang with us today, who will defend his licentiate thesis with the title Tiny Machine Learning for Structural Health Monitoring with Acoustic Emissions. Yuxuan has been working with us at the Department of Computer and Electrical Engineering for the last few years, pursuing his PhD studies, and is at the moment ready to present his licentiate thesis. So he has been working in our research group in autonomous sensor systems under the supervision of myself and Professor Bengt Ullman. And then we have with us today also on Zoom, on digital link, the opponent who will be responsible to discuss the thesis and evaluate the thesis of Yuxuan's. And as an opponent, we have with us Gian Domenico Licciardo from the University of Salerno in Italy. And we're very grateful, Gian Domenico, that you took your time to participate in the seminar. So very shortly, just for the process, we have, of course, as a first step, a short presentation of the thesis. So Yuxuan will have about 30 to 40 minutes to give you a summary of what his thesis is all about. And afterwards, we take a short break just to do some technical adjustments here before we go into the discussion between the opponent and Yuxuan. So this, of course, can take a while. The opponent has as much time as he wants to discuss the thesis until he's happy. And when that is the case, we will go to a separate meeting where the evaluator will basically discuss with myself and present his judgment. And then we'll come back to this room and announce the result of this defense. And finally, when all this is done, the seminar is over. We will gather in the S building for some cake and coffee. So without further ado, I'll hand over the word to Yuxuan. And maybe as a first question to Yuxuan then is if you have any errata to present, or if you want to defend the thesis as you have printed it. And if afterwards you can continue with your presentation. So thank you, everyone. Talk to you soon again.
Hello, my name is Yuxuan, and I will go through with the current version of the thesis. So good afternoon, everyone. Thank you for being here today, and I will present my research of tiny machine learning for structural health monitoring with acoustic emissions. I'm quite excited to share the achievements what we have made for now. So I will start now. So today I will give you a presentation about like 5 parts mainly, except the introduction, methodology, and conclusion. I will also introduce 2 case study, one for concrete material, another is for carbon fiber materials. So maybe you have a little bit of questions about what is structural health monitoring, and also the what is acoustic emission technologies mentioned in the title. And also in the introduction part, I will give you some idea about what is the current traditional AE-based structural health monitoring systems looks like, and how machine learning plays a role in structural health monitoring, and what's its limitations. And then it comes to the important part of this thesis. What is tiny machine learning, and what it can help with the current limitations. So what is the structural health monitoring? Basically, structural health monitoring is a process of implementing a damage detection strategy for structures like buildings, bridges, and other critical infrastructures. It involves the use of various sensors and data analysis techniques to monitor the condition of the structures in real time. It plays a vital role in ensuring the safety and the maintenance of infrastructure by continuously monitoring structure integrity. Structure health monitoring systems can detect early signs of damage, allowing for timely intervention before minor problems upgrade to critical failures. This is particularly important in preventing accidents such as bridge collapse, which you could have the figures on the left-hand side, or aircraft collapse, which could cause big consequences in terms of human lives and the cost, economic cost. On the left-hand side, we could also see there is a plain structure health monitoring system. It is a project from Clean Sky from EU Horizon 2022. They want to have a smart SHM system for aircraft and want to process the data as close to the sensor as possible. And that is also the main goal for our thesis or our studies. So in our studies, we use acoustic emissions, but why we use it and what is it? It is a technology that can detect transit elastic waves generated by the rapid release of energy within a material. Normally, like for example, you have a composite material board. It could be wood, could be concrete material, could also be a carbon fiber material. When there is some damage comes from inside, it will generate some waveforms. And then you could use acoustic emission sensors to detect the waveforms and transfer it to digital signals, which you could say here is a traditional waveform or example waveform for the acoustic emissions. It has a lot of advantages. It is a non-destructive testing method. It can provide real-time monitoring, and also it can provide early detection of the damage, and also the detections from non-visible damage. Which means for early detections, when the damage when you only have some small damage inside, you could use acoustic emission technology to detect it because it is quite sensitive. And that's the main advantage. But it also has a disadvantage. So the acoustic emission signals is very complex, and it needs a high sampling frequency. Usually it's 5 megahertz. So that's cause it's heavy to the computational resource. So what is the traditional AE-based structure health monitoring works? Normally it has 4 parts. You have the data collection part, the data pre-processing part, and the feature extraction and the classification. In the feature extraction part, normally we use a mathematical way, like a wavelet transform or fast Fourier transform to extract the time and frequency features. And based on the features, the experienced engineer could do classification to give the result for it. Currently, machine learning and deep learning has been quite popular in this area. The people want to use machine learning and deep learning to replace the last 2 steps to reduce the human cost in the whole structure health monitoring systems. But how is the current machine learning or deep learning based structure health monitoring works? Normally, the current solution is they use the one-dimensional signal as the original signal and then transfer to 2-dimensional images, like using the method like short time Fourier transform or wavelet transform or transfer to Mayo spectrogram, and then make them as the input of a traditional convolutional neural network, which is common usually for the image classification. But in that part, it will bring some problems because normally for science, it is quite heavy and the computational resource costs are also quite high. So what's the limitations for the current solutions for structure health monitoring? In principle, it is offline data analysis. You can't do it in real time. Even if you want to have a real-time structure health monitoring systems, the problem is that all data from the sensors has to be transferred to servers or cloud, then to run the data analysis or classification task. that will cause high energy consumption and high latency. Except that the small data set is also a problem for the machine learning or deep learning based algorithms, because these algorithms mostly are data driven. So how could we handle this problem? The tiny machine learning could help with it. So the tiny machine learning actually replace several parts of the original machine learning based structural health monitoring. The traditional is we use data preprocessing at microcontrollers, and then through Wi-Fi or Bluetooth or other communication method to transfer the data to cloud or server. But with tiny machine learning, we could replace all these three parts just on MCU, just on microcontrollers, bring the intelligence processing at the edge. In that case, we could reduce the need for continuous data transmission, and then to save the bandwidth, energy consumption, and also we could improve the latency. So now we can move to the research aim for the study. So this whole thesis is about to explore the feasibility and evaluate the performance of machine learning and acoustic emission-based damage classification on low-power, resource-constrained microcontrollers. The objectives include how could we develop and optimize the algorithms for structural health monitoring, especially for a low-power, resource-constrained device. And then we will investigate the impact of model complexity and data sets on the performance. Also, when we have the model, we want to explore the generalization of the model for different data set, and then we want to give some comparative analysis about the data augmentation part, because we mentioned before the small data set is one of the big problem for this. So for the methodology, I will give you a overall approach and of the thesis of the whole work, and then I will give you the workflow for traditional machine learning or deep learning method, and then I will introduce the evaluation metrics that we used in our thesis. So basically, this thesis is consists of 5 papers. So from the beginning, we start with convolutional neural networks with raw acoustic emission signals, which is one-dimensional signals. We want to replace you could say, we want to reduce or remove the part of transition from one-dimensional to two-dimensional. And then we go even further. We go to artificial neural network and random forest with raw acoustic emission signals to try to improve the inference time and try to reduce the memory consumptions and power consumptions. And then at the end, we go even further with feature extraction with artificial neural networks. The paper consists 2 parts of dataset, which you can see from the right-hand side. From paper 1 to 4, we use the concrete dataset, and the paper 5 used the carbon fiber dataset. Then I will introduce the dataset what we used. So for the concrete material dataset, it is from University of Catania. It is a public dataset. It has 15,000 samples. For each sample, it is 1,000 by 1 data points. There are 3 classes in the dataset, the tensile, shear, and mixed tensile and shear. Each class has the same number of samples. And for the carbon fiber dataset, it is from Cardiff University. It only has 207 samples. The original data sample has 4,096 by 1. And there are only 2 classes in the elimination and matrix cracking. When it comes to the normal machine learning and the deep learning approach, so it's divided into these several steps. So first, you have to define what is the problem. It is a regression problems or it is a classification problems. In our case, it is a classification problems. And then you go through the collection part, the pre-processing part, the algorithm, selection, training, optimization, testing, and then at the end, deployment. The evaluation metrics we here used is like for all the machine learning algorithms or other papers, we use accuracy F1 score, precision recall parameters and the flops. Specifically for tiny machine learning, we introduced the RAM flash usage, the inference time, and the energy consumption per inference. So then I will introduce the case study 1, the concrete material. For data pre-processing part, we used a standard scaler, which can remove the min and the scales features to unit variance. And then we use the raw signals 1000 by 1 as the input for the algorithm. So at the beginning, we designed a lightweight one-dimensional CNN network. The structure could be checked at the left-hand side. And then just want to emphasize for this study is that what we achieve here is that our model, compared to the previous one-dimensional convolutional neural network, which we has the very less parameters, flops, and at the same time we achieve a very high accuracy at 99%. That is quite good and acceptable. And then it comes to the feasibility of microcontroller deployment. The working flow for the deployment is we use TensorFlow to train the model, and then we use TensorFlow Lite to convert the model and optimize it. For optimizing, what we use is quantization from a float point model to int point model, which can reduce quite a lot of memory usage. And then we use TensorFlow Lite for microcontroller and response IDE to deploy it. For the deployed result we have here is it still achieves 99% of accuracy, and it only requires 60 kilobytes RAM and 30 kilobytes flash, with inference time at around 160 milliseconds, which is kind of acceptable, but still a little bit, it will still introduce a little bit of latency for the real time. The energy consumption per inference is just 0.5 millijoule. Then after this feasibility investigation, we try to squeeze the network or simplify the algorithms. Then it comes to mostly the second work, the self-designed lightweight artificial neural networks. What we have here is this is the structure of the self-designed lightweight ANN. It could also achieve acceptable accuracy. It's like 98%. For the model complexity, we could say it reduced quite a lot from 20,000 to 20,000 to just 4,000 parameters. So that makes it more faster on the deployment on the deployment part. On the deployment part, we are not only deployed on just one microcontrollers. We deployed on several microcontrollers, which you can see on the table right-hand side. And then when it comes to the performance, we can say here it is much faster and much faster than the proposed model. The 24 here is the previous work, the proposed one-dimensional CNN. And then we also explore the different inference time and energy consumptions here. But the thing is, even we have a acceptable or a very fast model or deployment result, but the accuracy decreased a little bit to 98%. In real-world applications, normally the industry will need at least 99% of accuracy. So we are trying to maintain the model or trying to maintain the inference time quite fast at the same time, and then try to maintain the accuracy above 99%. Then we introduce the feature extraction part with artificial neural network. This is the third work. So there are 28 features extracted from the beginning. It is divided into basically main 4 parts: the statical, the time domain, frequency domain, and wavelet domain. But as you know, 28 features is too much. So we're trying to use some of these features. Then we introduce the selection method for a feature. We used here is the chi-square test and multi-information. But it comes to some problems. From the left-hand side, we could say that for both methods, there is quite a lot of difference between both of them. So it's really hard to decide which features should we select. Then we investigate a combination of the features by recursive feature elimination with a decision tree. And finally, there are two groups we selected. The first one contains 6 features. The second one contains 8 features. We use them as the input of the artificial neural network model. For the model structures, we didn't use the previous self-designed model. We want to have a more accurate result, so we introduce a TensorFlow Keras Turner optimization method. It is a built-in function from TensorFlow, which can it's more like an AutoML structure method that can search the structures for a high accuracy. At the end, we have 2 of them. The first of them also is searched by this method. So based on here, we can see 3 of these models. All of them achieve 99% of accuracy, but with a little bit the parameters, bigger than the previous one. But when it comes to the inference time, we found that on the resource-constrained devices, it is quite time-consuming for feature extraction. We didn't think about it before. So what we have here, you can say, is for 6 features and 8 features, the feature extraction time takes like 470 microseconds to process the feature extraction process, and the inference time only takes very few. So in this case, we have to say it really depends on what is the crucial element for you to decide. Like the memory so important, or is the accuracy important, or the inference time is the most important thing. So that's the case study 1, and then we go to case study 2 with a very small data set. We use the same data preprocessing process with standard scalar, and then we want to use the same model we proposed in previous study, the CNN model. So we do the subsample for the original signals to 1000 by 1. Other than that, because of the small data set, we introduced several data augmentation methods. So originally, there are only half of the data is used to do the data augmentation to 2000 samples for each class. We introduce several methods here for jittering and scaling, which are quite similar. They basically add random numbers following a normal distribution centered around the mean with a standard deviation to the original signal. And for magnitude wrapping, the amplitude of the signal is, because it's a nonlinear adjusted over time to the original signal. And for time wrapping, we use the time axis of the signal to create some temporal variations to the signal. And then the permutation is just the permutation is a process where the segments of a signal are shuffled in a random order to reduce the variations while maintaining the overall signal structures. But here we could say the quality is not that well, so remove this method in the rest of our study. And for random sampling, it's also quite easy to understand, just random sampling from the original signal. And then we also use to add Gauss noise at a specific signal to noise ratio at 95. And also we introduce a deep learning method, which called deep convolutional generative adversarial network. It's a type of convolutional network consists of a generator and a discriminator, and used for generating realistic synthetic data by learning the underlying data distribution. For the deployment, or for the algorithms, what we use, except the previous study proposed one-dimensional lightweight CNN, we also introduced 13 other machine learning algorithms, selected through the PyCaret, which is also a kind of AutoML tool. On the right-hand side, we can see the table here. The random forest classifier has the best result. But for the convolutional network, because of the small data set, it is overfitting, which means not work. But as I mentioned before, we introduced the data augmentation method. So when after the augmentation, we have the result here, which is also the deployment result. Both of random forest and CN, we achieve 99% of accuracy. But the flash size of random forest is way higher than CN because of in random forest we use quite a lot of tree nodes here. But for inference time and energy consumptions, we can say random forests have a very big advantage rather than the CN one. Except from this table, we could say random forest is kind of the best, but is it really the best one? We also did some investigations for the impact of data augmentation. So we could say the figures here. We try to evaluate the robustness of the model and of the model with data augmentation. There is two methods here. The left is the random forest, and the right is the CN model. We could say for both of the model, when you use the DCGN, the deep learning data augmentation method, you will have a very good robustness for the performance. But when it comes to the difference between two models, we could say here basically for random forest, when the noise start to increase, the accuracy decreased very fast. But for CN models, it performs quite well until the signal to noise ratio equals to 55 or 45 dB. So in this case, I will say it's really hard to say which one is best. If you want to have fast inference time or you want to have low power consumptions, you could go with random forest. But in real industry applications, there will always be lots of noise. So the robustness will be a key thing for that. Then the CN should be better. And then I will give you the conclusions and the future works for the thesis. So basically, we successfully deployed the lightweight machine learning models on low power resource constrained microcontrollers for real-time structural health monitoring. And also we found that the CN model is quite okay with both dataset. Means it gives it a generalization ability. And at the end, it's quite hard to have a best model for the acoustic emission-based structural health monitoring systems. We can see from different point of view, from accuracy, we have the random forest and the AN with feature selection, and CN are quite good. But for inference time, the random forest and AN we self-proposed are the best, you could say. But for robustness, the CN is much better than the random forest. And also in terms of RAM usage and flash usage, which is quite a key point for the resource-constrained microcontrollers. We could say the self-designed AN requires the least. And also, except the details, what we achieved here, we also make some impact for both industry and academia. For industry, our research could improve the infrastructure safety and to reduce the cost and bring the real-time monitoring to the industry. Also, the energy efficiency. For academia, we contribute to the development more effective and efficient for structural health monitoring methodologies, and we provide a valuable case study for deploying AI on resource-constrained applications. And we also open new research opportunities. Once we have achieved the deployable machine learning algorithms on resource-constrained devices, it means we could also make it to other applications. And also, this research could be a benchmark for future studies. for the tiny machine learning based structural health monitoring systems. And in the future, there are still some questions to be answered, I would say. So this first thing is, would that be possible to further optimize the machine learning algorithm architecture for even more lower power consumption and faster? The second is, would that be possible to integrate the data acquisition part with the machine learning inference part? For now, our systems only includes the machine learning inference term or the classification task. But normally, you will still need a data acquisition system separately. So in the future, it is quite interesting to integrate both of them. And at the end, we only investigate 2 data sets. So it is quite interesting to expand the data set to include more diverse type of damage and the materials to verify the model generalization ability. And that's basically all the studies what I have done for now. And thanks for listening. Do you have any questions or?
Okay, great. Thank you very much, Yuxuan, for this presentation. So at this point, as I introduced in the beginning, we will take a short technical break. At this point, we will also end our streaming on YouTube. So thank you everyone for listening there. And the discussion with the opponent will continue in 10 minutes on Zoom and in the room only. So thank you very much everyone, and we'll be back soon.